Good morning, everyone. Today we'll be discussing about principle of conservation of linear momentum. This is my third lecture of the lecture series Laws of Motion. So, conservation of linear momentum. So, for an isolated system, external force applied is zero. So, when we are considering a system which is isolated, for an isolated system, external force applied is zero. So rate of change of momentum dp by dt equal to 0. So P is constant. P is constant. So momentum is conserved because derivative of constant quantity is 0. So for an isolated system, momentum is conserved. Momentum is conserved. So now let us consider an example of conservation of linear momentum, that is recoil of gun. This is a very common example. Recoil of gun, and quite interesting also. When a bullet is fired from the gun will recoil back with some velocity. Let's say m is the mass of the gun, or mg is the mass of the gun, and vg is the velocity of the gun or speed of the gun, velocity of the gun. Now mb is the mass of the bullet, and vb is the velocity of the bullet. mb is the mass of the bullet and vb is the velocity of the bullet. So when we are firing a bullet from a gun, it is considered as an isolated system because external force applied is zero, because the amount of force we are applying in this trigger is very very small. We are not kicking this gun to make the bullet fired, or we are not hitting this gun with a hammer or putting extra force to fire this bullet. We are simply touching the trigger, very very little force, so we can consider it as an isolated system. So since it is an isolated system, so external force applied will be zero. So what we can write? The momentum of this system remains conserved. So what are the momentum we are getting? We are getting momentum per bullet plus momentum per gun equal to 0, because in my previous lecture I have mentioned that momentum is a vector quantity. That's why I'm using a vector symbol here. For vector things, you can check my vector lecture series. So now I can write momentum of gun is equal to minus momentum of bullet. So for momentum of gun, I can write mass of gun into velocity of gun, because momentum is the product of mass and velocity. So mass of the gun into velocity of the gun equal to sorry, minus mass of the bullet into velocity of the bullet. Mass of the bullet into velocity of the bullet. So, if bullet is fired in positive x-axis, now gun has to recoil in negative x-axis. Negative x-axis. So, gun will recoil backward, or gun will recoil in a direction opposite to the direction of the bullet. So, this is positive x-axis. And uh, of course, mass of the gun is very very higher than mass of the bullet. So velocity of the gun should be less than velocity of the bullet. Velocity of gun should be very very less than velocity of bullet. Else there is no point of firing a gun, right? So hope you have understood what is conservation of linear momentum in terms of recoil of gun. Now quickly we are going to the most fascinating topic of laws of motion, that is drawing free body diagram and understanding various diagrams, solving pulley problem, solving lift problem. These are very very interesting concept. Hope I could be able to write all the uh, mathematical modeling and including the diagrams of free body in this video, and thank you for your patience. Please give your feedback in my comment section. Watch this video, like and subscribe, and share also. Please share it to student, so that student will get benefit. And I personally believe if we distribute lessons, then we'll learn lessons. Learning is only possible through three things. One is distributing among friends, juniors and seniors, interacting with your faculty members, and also uh, uh, teaching. If you can able to teach to your junior nearby, then you start teaching, start discussing some physics, start solving some problems. Okay, so now we'll be quickly moving to this free body diagram. Let us consider a block or a book is on the table. This is a table. The book is on the table, rest on the table. This is a book. Let's say the mass of the book is m. M is mass of the book. So the book will give a force to the table, that is mg, that is weight of the book. W equal to mg. So weight is a force, weight of the book. And always remember, weight is always vertically downward. Weight is always directed vertically downward. Weight is always, this is important, vertically downward. Weight is always vertically downward. So W equal to mg. Now, according to Newton's third law, every action has equal and opposite reaction. So book is giving a force, that is its own weight, to this table mg. Now table is also giving an equal and opposite force, or equal force which is acting opposite to this, acting opposite to the direction of weight, that is normal reaction. In many books you can find normal reaction is taken as n, but I'm taking it as r. So r is normal reaction, which is always perpendicular to the surface. Normal reaction which is always perpendicular perpendicular to the surface. Normal reaction is always perpendicular to the surface. Look, this is the surface. Now this is perpendicular. Normal reaction is always perpendicular to the surface. So at equilibrium, equilibrium means if I am putting this book and the table is not breaking, or if the whole system is not going higher, going above the ground. So at equilibrium position, the net force will be zero. So what are the net force on this book? Mg is vertically downward, R is upward. So I can write Mg minus R equal to zero at equilibrium. So Mg equal to R. This is the equation written from this diagram. So the beauty of this topic is draw free body diagram, FBD, free body diagram. Find what are the forces acting on that particular system and how they are related. Here this book is having two forces. One is its own weight, another is facing or experiencing a force, that is normal reaction from the table. So at equilibrium, since the table is not breaking, mg minus r equal to 0, so mg equal to r. So quickly we'll be moving to some other diagram to understand what is free body diagram. And don't get panic, even if I'm making a little bit faster teaching, just pause my video and you can uh, note. But I don't believe you should write notes. It's better you should watch this video and try to understand. Understanding is more important in physics than that of writing notes. Okay. So now I have already mentioned. Let me write again. This is the table. This is the book. So weight is vertically downward here. Normal reaction is perpendicular to the surface always. So R equal to mg here. Now I am suppose considering an inclined plane, but it is smooth. I am considering a smooth inclined plane because this is the topic that will lead to friction. So smooth inclined plane. So since I'm talking about smooth inclined plane, let's say this is the block. So what are the forces on this block? I have already mentioned the weight is always vertically downward. So this is the weight which is always vertically downward. And this is the normal reaction which is always perpendicular to the surface. Many people are trying to do normal reaction like this, but this is wrong. Normal reaction is always perpendicular to the surface. So I can draw some more surface to show you what is normal reaction. So normal reaction is always perpendicular to the surface. Now if I draw this, if this is theta, this will be theta according to similarity between triangles. So no need to worry much. Now mg, this is mg, theta is attached to this side, so this has to be mg cos theta. And if I draw a rectangular component or perpendicular component to this will be mg sin theta. So what are the forces acting on this body now? Now you can say R is exactly equal and opposite with this mg cos theta. So blindly I can write R equal to mg cos theta, because now the plane is inclined by an angle theta with this horizontal here. R is exactly equal to mg, but here the case is different. R equal to mg cos theta. And what are the other forces? One is mg. Mg is already broken into two components, mg cos theta, mg sin theta. Now the block start moving downward. So what is the net force on this block? Net force on this block is F net equal to ma, because from Newton's second law, F equal to ma, and ma is equal to mg sin theta. So cancel, a equal to g sin theta. So the book will climb downward or move downward with an acceleration g sin theta. Book will move downward with an acceleration g sin theta. If you compare this, suppose here is a book. You are, you have hold a book in your hand. Now you are freeing your hand. You are leaving this book. The book will fall with an acceleration a equal to g. But since the book is moving downward through this surface, which is making an angle theta, now the net force on this book is mg sin theta. So acceleration of this book is g sin theta. A equal to g sin theta. So thank you for attending this lecture. I'll be coming with more free body diagram in my next lecture. Thank you for your patience. Please subscribe and share my video to students so that they will be benefited.